Hello, everybody. Today, what I want to do is nothing explicitly new, but I want to give you the opportunity to kind of compare the different methods that we've been doing with the integration. Because at the end of this course, I don't want to baby you. So I'm not going to give you an integral at the end of this course and say integrate by doing u substitution, but rather, if I give you an integral like, let's say that I give you, and I've actually done this before with previous calculus classes, so I give you like the integral of, 5x squared plus 2x to the 66th dx, and I've actually given a purposely large exponent like that. But what I've tried to develop in my students is the ability to kind of determine that you need to be using the u substitution method for that. So we're going to be talking about when do we use the four methods and how do we use those four methods. And at the end of the day today, you're going to have a really nice graphic organizer that's going to kind of help you with the general integrate blah 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 type of questions. So I'm going to attach a blank copy of a organizer on the Haiku page that's going to look something like this. And in this presentation, we're just going to kind of go one at a time. So I'm actually going to work off of kind of some filled in that I have. And but I'd like you to kind of get the experience of paying attention to this presentation and copy down what you see. So, just a reminder, this symbol that looks like the violin symbol just means take the antiderivative. And the first type of antiderivatives that we did were sort of those well-behaved antiderivatives where I had a coefficient variable exponent, and what we kind of saw was you would just generally, we had a standard polynomial that was definitely a conventional power rule. Whenever we had exponents in the denominator, like on this example, we wrote that as a negative exponent. So if I had like 1 over x to the third, I would write that as x to the negative third. And when we had radicals, even though radicals, look all ugly, at the end of the day, they can fit nicely into that conventional power rule as well. So always remember that square root of x is the same thing as x to the 1/2. And this number that's inside of a radical is your numerator in your exponent, and the number that is outside of a radical is the denominator. Now, a lot of our integrals that are not as well behaved are those u substitutions. So when we see parentheses and it starts looking like we have to do lots of polynomial multiplication, 2 maybe is okay to, multiply out and turn it into a conventional power rule problem. But if I have, large exponents, even like a 3 or a 4, I think it's really time to get to that u substitution. Also, radicals, with expressions inside, and the natural log and the e stuff, really takes to that u substitution. So stuff that you would really be using the chain rule for. Of course, you want to also look back in your notes and think about maybe some trig cases as well. And we kind of went through, what those trig integrals were. But those are, kind of the main tools that we have for those integrals. All right, the first type of integral that we learned was the indefinite power rule integral. So this was, taking the antiderivative, increasing the exponent by 1, and dividing the coefficient by the new exponent. If you want kind of an example, let's say that I have x to the 1/2 dx. We can add 1 to the exponent. Now, I kind of chose an example like this because some people still get a little caught up with the fractions. So I just like to write, 2 over 2 to make it equivalent to 1 when I'm adding 1 to that exponent. So I'm at x to the 3/2. So if your coefficient is 1, well, we want 1 as our coefficient when we take the derivative. But a quick way to get to that 1 is just think about what the reciprocal is of 3 over 2. So we could say that that's 2 over 3. Now, if I had a different coefficient, like let's say that I had a coefficient of 2, in my original problem, I could just take that 2/3 and multiply by 2 to get 4/3. And of course, you want to make sure that you are adding a plus c at the end. Next, we have the indefinite u substitution integral. So this would be, like that example that I wrote, like let's say I had 2x squared plus 3x to the 66th dx. So this is where, it pretty much shouts u substitution. So you're always going to be finding the u and then doing the du. Make sure that you're including a dx. And of course, I'd try to, get you into a situation where we have, some stuff on the outside that you can easily adjust. Here I was just kind of making an example up on the fly. But I'll give you, u substitution examples usually that work pretty well right off the bat or with a little bit of an adjustment. You want to make sure that you're taking the antiderivative then with respect to u and then plug the u back in. So, realistically, I think with the example that I made up, I'd probably give you something like, and then I would have the dx, the du on this one, like the 4x plus 3 dx. So that way you could just write this integral as u to the 66th times du. And then you could just do, that antiderivative respect to u. And then, of course, when you're done, we like you to make sure that you're plugging that u back in terms of x. And adding the plus c in. So I think that goes without saying that there's a plus c. When we get to definite integrals, that's when we can kind of get rid of that plus c in the final answer. All right, the next case that we have are the definite integrals. So the definite power rule integral, we take the antiderivative, then we basically plug in our b, we plug in our a. So you always want the b to be bigger than a. And you subtract the two results. If you have a situation like let's say, I had an integral of some stuff. I'll just call this stuff. And maybe I did, 2 to 0. You could just put a negative sign in front and get it to, be a well-behaved integral like that. So that's what we're kind of doing, with those definite integrals. And last but not least, we have the definite u substitution. So there's some choices that we kind of talked about last time, and get that in depth. Just go to the last lesson, and you can see that there were 2 methods side by side. The method that I like is, once when you find your u, you can plug in your upper and lower limits into your u to change the limits of integration. So if I had, 0 to 3, maybe I would find u sub 0, u sub 3, and we would get, some numbers, and then we could, change that limit of integration when we write the integral in terms of u. And what's nice is that you don't have to change it back to x. Now, if you want to, you could, pretend like it's a indefinite u substitution. That's fine. But the problem with that is you do have to plug x back in, and you'll kind of get maybe some number crunching that you have to do, and it won't look as nice. So your practice today, I'm going to change the directions to just integrate. So I'm going to purposefully mix together indefinite, definite, and u sub, regular power rule, because I want you to be comfortable with the directions of integrate. So thank you very much, and happy integrating.